I'm pretty sure that most of us are aware of the Rolls Royce Merlin engine, the driving force behind so many of the most important aircraft of World War II, like the Spitfire, Mustang, Hurricane, Mosquito and Lancaster, to name just a few. But behind the scenes, another Rolls Royce engine was poised to take on what had been done with the Merlin and move it on significantly, with a radical design that not only made the Merlin look simple by comparison, it was also much more powerful, and for its 26 litre capacity it had the highest specific output of any Piston Aero engine then or since. This is the story of the Rolls Royce Crecy, a revolutionary two-stroke aero engine, and what might have become of it if it had been just a few years earlier. This video is sponsored by Brilliant. The story of the Cressy starts in the mid-1930s. This was at a time when Germany was rearming and the build-up of its Luftwaffe was causing concern amongst the British government and military. The plan at the time was to have aircraft patrolling along the coast at altitude on the lookout, but there was a limited number of them available and they could only patrol for as long as they had fuel. As trials of the early British radar progressed, it showed that there would be an opportunity for a high-speed sprint engine for an interceptor fighter that would be able to take off and climb quickly to confront any foreign aircraft to augment the regular patrols. In 1935, this was suggested by Henry Tizard, later of the Tizard mission to the US, at a meeting of the Aeronautical Research Committee, or the ARC, of which he was the chairman. He asked the question that if such an engine could be made, could they disregard the fuel and oil consumption to gain very high performance for short flights only? At the time, aero engines were big but not that efficient. The specific power output of a Pratt & Whitney Twin Wasp, for example, which was one of the most common engines of the time, was 0.66 horsepower per cubic inch, and just making them bigger with more power didn't fix the power to weight ratio. So new engine designs and materials would be needed to make lighter, more powerful engines. On both sides of the Atlantic, there was a race to produce a hyper engine that had a specific output of 1 horsepower per cubic inch. Tizard was a good friend of Harry Ricardo, now regarded as one of the foremost engine designers of the 20th century. Ricardo had been working on a sleeve valve, two-stroke compression ignition diesel aero engine that could equal the output of a conventional petrol aero engine for several years. A couple of months after the meeting of the ARC, in a letter to Tizard from Ricardo, he suggested that his diesel engine could be converted to a spark ignition to produce an extremely high output engine with a small frontal area. This engine would become the Cressy and be developed by Rolls-Royce and Ricardo's company. As Tizard was overseeing all engine development through the ARC, he was also encouraging the likes of Hayne Constant and Frank Whittle as they worked on the early turbojet engines. So the development of both jet engines and advanced piston engines was seen as the best approach to deal with the future threat from the Luftwaffe. Ricardo thought that the more traditional poppet valve engines, like the Merlin, with 2 valves in the cylinder head, would be unlikely to make more than 1,500 horsepower because there is a limit as to how big the valves could be in relationship to the cylinder, and thus how quickly the air-fuel mix and exhaust could be got in and out of the engine. He had already published a study on sleeve valve engines in 1927 and thought that these will be the next generation as they offered greater volumetric efficiency. Now you may be forgiven in thinking, what is a sleeve valve engine? Well, they are a very different design that became popular in luxury cars around the 1920s. Instead of the 2-valve cylinder head design that we think of as normal now, the piston goes up and down in a sleeve which has holes cut into it which work as the inlet and exhaust valves, a bit like a 2-stroke engine, but with a difference. The difference here was that the sleeve itself then moves up and down and from side to side to line up the inlet and exhaust ports with the cutouts of the sleeve as the engine goes through its 4-stroke cycle. This sleeve allows for multiple larger ports that would be bigger in size than the valves in the cylinder head design, and consequently the engine can breathe better. It also made the engine less susceptible to pre-ignition or detonation due to the poor quality of the fuel at the time. But there is a downside to these engines. The gearing mechanism used to make the sleeve move up and down and from side to side in time with the piston makes them very much more complicated. It's not too bad in a single cylinder engine, but in a V12 or rotary there are a lot of extra cranks, shafts and gears involved. Sleeve valve engines were used in other aero engines during the war. Frank Halford, who worked in Ricardo's London office from 1919 to 21, went to Napier to design the 24-cylinder Sabre sleeve valve engine, which went on to become one of the most powerful engines of the war, and that was used in the Hawker Typhoon, whilst Ricardo worked with the Bristol Aeroplane Company to design a range of rotary sleeve engines for the Bristol Beaufighter. The difference between those and the Rolls Royce Crecy was that the Cressy was a two-stroke with petrol injection and a unique variable thrust supercharger. The simplicity of the two-stroke design combined with the sleeve valves could be a game changer with power outputs of up to double that of a normal four-stroke engine. Ricardo's company did most of the development work on single-cylinder and V-twin engines, the V-twins being of particular use with the sleeve valves. This was normal to work out the best design before building multi-cylinder engines like a V12. One of the unique features Ricardo created was a cone-shaped cylinder head with a bulbous upper chamber, with two spark plugs and a central fuel injector at the top. This bulbous chamber allowed the fuel air charge to pre-combust in a rich mixture around the spark plugs before spreading out to the rest of the weaker mixture in the remainder of the cylinder. This allowed it to run on lower octane fuel or at higher boost pressures without detonation, something which held back a lot of other engine designs during the war until fuel octanes of 130 to 150 were available later on. As the Cressy was a two-stroke, when the V12 was running at its full speed of 3,000 RPM, there will be 36,000 exhaust pulses per minute, twice that of a four-stroke engine like the Merlin. So it really would scream like a German Junker Ju-88 Stuka dive bomber, which used two wind-driven sirens known as the Jericho trumpets to create that characteristic scream that would scare the living daylights out of anyone on the ground. The Cressy's exhaust would do that all by itself. There was another advantage to the sleeve valve in that the opening of the ports could be done with an eccentric gear, so that it opened very much faster than that of a typical overhead valve driven by a cam. The effect of this almost instant valve opening was to make the exhaust gas exit much faster, which combined with the double frequency of the cylinder firing gave the Cressy up to 350 pounds of thrust just from the exhausts. The Merlin engines also used exhaust thrust but was only able to achieve about 150 pounds of thrust. At 300 miles an hour, each 1 pound of thrust was equal to 1 horsepower through an 80% efficient propeller. This explosive exhaust and doubled frequency also made it extremely loud. It's a pity there's no footage or audio recording of it of when it was being tested, as it was said that when it was running on the test stand it could be heard over 5 miles away, and when they first started testing it, it triggered the air raid sirens 15 miles away. On December 21st, 1944, Cressy engine number 10, a V12 26.1 litre engine, achieved 1,798 horsepower from a normally aspirated engine running on 100 octane fuel. When the calculated blower power was added, it would have been 2,350 horsepower, but once corrected for the test stand losses, it was about 2,500 horsepower. If you compare that to the most powerful Merlin derivative, the Griffin, which was 37 litres, 11 litres bigger than the Cressy, and running on 150 octane fuel with a two-stage supercharger to the Cressy's single blower, that produced 2,220 horsepower. Again, if you compare the specific output of the two, the Cressy was 1.77 horsepower per cubic inch to the Griffin's 0.91 per cubic inch, easily beating the 1 horsepower per cubic inch goal of the Hyper engine. Tizard, talking in 1946, said that the research had shown that the two-stroke sleeve valve engine was capable of nearly 200 horsepower per litre, a figure which is only beaten today by the highest performance race engines running at very much higher RPMs. As the Cressy was a 26.1 litre V12, its fully realised output could have been 5,000 horsepower, double that of the best performing four-stroke engines. So what happened to such a powerful and important engine? Well, basically it arrived just too late, and it had been a low priority throughout the war, with design and manufacturing talent being assigned to more important tasks such as building and improving the Merlins and their derivatives, because they were used in so many of the RAF aircraft and others during the war. Because of its extra complexity, it was unreliable and broke down many times, but it has to be remembered that this was still under development, and it combined a lot of different technology in newly developed metals in one engine, something which hadn't been done before. It was due to be tested in a Spitfire, but it was found that the Spitfire's airframe wasn't strong enough to handle the power. So a P-51 was thought to be a more suitable match for the engine, but no further action was taken. So instead, it was to be flight tested in a Hawker Henley, but when no engine became available, the Hawker test aircraft stood idle until the end of the war, when it was scrapped. By 1945, it became clear that the jet engine would become the future, and resources were moved towards that and away from the Cressy. Because of its high fuel efficiency, there were plans to use it in civilian transport after the war, but again, the development of the jet put paid to those plans. Just 6 full-size V-12 Cressys were built and 8 V-twin test engines. The V-12s ran for a total of 1,060 hours and the V-twins for 8,600 hours, but all of them only ever ran on the test stand. Cressy No. 12 was to use a shaft-driven exhaust gas turbine blower, which was a half-scale WR1 turbojet, as a power recovery device to make use of the exhaust thrust, as well as the variable thrust mechanical supercharger, which would have made it more fuel efficient for larger transport aircraft. The back pressure created from the turbine would also have worked to increase the power of a two-stroke, whereas in a four-stroke it would have lost power. But by then, Rolls-Royce had decided it was just too much effort to bring the Cressy up to the reliability of the Merlin, as the market for high-power piston engines waned at the end of the war and the jet engine took off. So the Cressy became just an interesting footnote in the history of aviation. What happened to the 6 Cressy engines is unknown, but to date, none have been found complete or in pieces. In a letter to Ricardo, the Cressy project engineer Harry Wood said that if it had been given another 6 months of development, it would have not only been much more powerful, but reliable as well. It's also said that if Whittle and von Hain, the designers of the first jet engines, had been born 10 years later, the Cressy would have been the fill-in between the Merlin and the jet engine. In the race to create the best aero engine of the war, it wasn't just the Cressy that lost out, it was the piston engine itself. Jets just did a better job, which was proven by history. But it was only through the dogged determination of a few highly skilled engineers like Frank Whittle and Hans von Hain that this came about. Now, skills and thinking out of the box are something our sponsors of this video, Brilliant, can help you with. Brilliant is a fun problem-solving website and app, so you're not tied to the desktop, and you can help develop those learning skills anywhere. Research shows that doing active problem-solving is more effective than sitting and watching a lecture or a video. Brilliant's approach is based on this active problem-solving and learning method. It's about seeing concepts visually and interacting with them so that you can remember them. Their courses are created by award-winning teachers, researchers and professionals from the likes of MIT, Caltech, Duke, Microsoft, Google and more. The courses are laid out like a story and are broken down into pieces so that you can tackle them a little bit at a time. There's no big deal here. There's no tests or grades to take. If you make a mistake along the way, you just need to check out the explanations to find out more. Brilliant has something for everybody, whether you want to start with the basics of maths, science and computer science, or dive into the likes of something like neural networks or quantum computing. So if you want to support curious-droid and join a community of over 9 million learners, you can get unlimited access to all of Brilliant's in-depth courses and learning by heading on over to brilliant.org/curious-droid and following the sign-up link. So I hope you enjoyed the video, and if you did, then please thumbs up, subscribe and share. And I'd just like to say a big thank you to all of our patrons out there for their ongoing support.